Hello again. Welcome back to grade 10 academic math. We're going to do a kind of double lesson today. In the course, the way it's set up, similar triangles is split up into two lessons, lesson 13 and 14. And I think it's actually a bit much for similar triangles. Similar triangles are important. It's the building block of trigonometry. It's the stepping stone of how to get to trigonometry, but I don't think it really is that much material. So I kind of squeezed all the stuff together into this one video for both lesson 13 and 14. So what do we mean by similar triangles? What's that word mean? What is similarity? Mathematically, when we say similarity, it means uniformly scaled. In mathematics, the term similar, or the property of similarity, refers to the shapes that are uniformly scaled. Uniformly scaled, what does that mean? That means that when I make it bigger or smaller, I'm making all of the various dimensions, length, width, depth, whatever, however many dimensions the size is, the shape is, right? I'm making them bigger or smaller by the same amount. Okay, so there's some scaling factor. I'm multiplying the length by, I don't know, in this case, what's it look like 2 or something. I'm doubling the length and I'm doubling the width. So if I double them all together, they're the same shape, right? We're not compressing it along one axis or something like that. We're not changing its shape. We're just zooming in or zooming out onto that shape. So when we say similar triangles, it just means I take my triangle and I can make it bigger or smaller. Now, a property of similarity is that it's invariant to rotation and reflection. Those are some big words. Okay, invariant. What does that mean? That just means it doesn't matter. It doesn't care. Let's say I take my triangle and I rotate it. So I rotated it about, I don't know, what's that, 110 degrees or something like that, 100 some degrees to the right. I've taken that shape and I've spun it. That doesn't change the similarity property. It doesn't change the how the shapes changed. I've only done rotation. I haven't changed the scaling in any way. Similarly, I could take it and rotate it. I flipped it on some vertical axis here. Sorry, I've reflected it. I haven't rotated. I've reflected it. So it's invariant to rotation. So this one here, this is a rotation. And this here is a reflection. So it doesn't matter. It doesn't care. The scaling doesn't care if I reflect or rotate. Now, if I take my triangle and I make it bigger vertically, but then I don't change horizontally, this is not a similar triangle. Okay, the length, the proportionality of the lengths is no longer the same. Okay, so in geometry loves sort of laws, axioms they call them, a sort of rule that you have to follow. So we can say the two triangles are similar if they follow these two laws, these two rules, these two axioms. That's a really good word. It's a mathematical word. Axiom. I like it. So two triangles are similar if the corresponding angles are all the same. So that means in this guy here, so this angle is the same, this angle is the same, and this angle is the same. By same, I mean, if we took a protractor, I mean, measured them, they'd be the same. And another way another rule that we have to follow is that the corresponding sides are proportional. That was a little bit more complicated. So let's take it a little bit more rigorously here. So let's say we have triangle ABC and we have a triangle DEF. So if we say that angle A is equal to angle D, angle B is angle to E, angle C is equal to angle F, then we can say that therefore triangle ABC is similar. We're going to use this tilde here. That's if you go shift the key next to the 1, to the left of the 1, and you go shift that thingy, you get a tilde. And if you use equation editor, it'll spit out this little wavy line that means similar. So this is saying that the triangle ABC is similar to triangle DEF. That's one way we can say they're similar. Or we can say that their sides are proportional. So let's give them some numbers. Let's say ABC has sides A, B, and C. Now notice, okay, so this is just a very common convention mathematically for labeling sides, especially for triangles. Angles are always capital letters. Okay, angles are capitals. Notice that the angles here, we have capitals. That's with an O. Capitals. That's not, doesn't even look like an O. I apologize. And the side lengths are lowercase. Okay, so side lengths are lowercase, angles are capitals. And that's just a convention we use. So we've assigned some lengths to these things. Now, corresponding sides. So A here corresponds with D. So when we divide them, D over A, 6 divided by 4 is 1.5. So we're saying that the side length D is 50% larger than the side length A. That's another saying. Or we can more simply, to get the length of D, we multiply the length of A times 1.5. Similarly, F corresponds to C, so it's just 12 over 8, and E corresponds to B, which is 9 over 6. And all of these correspond to, all these proportionalities, how much bigger they are than each other, are all the same. So I've taken each side length of ABC, I've multiplied them by 1.5, I made them all 50% bigger, and I end up with triangle DEF. So since all these proportionalities are the same, we can say that triangle ABC is proportional to triangle DEF. Okay? So either all the angles are all the same, or all the sides are proportional to each other. So let's try a problem here. Let's say I have these two nested triangles, ABC, that's the bigger triangle, and inside that I have another triangle, ADE. And notice that side length BC and side length DE are parallel to each other. That's what those little arrows mean, right? That they're parallel. It also tells us that AB, this longer length here, is 36. Okay? And it asks us to find out what the length is of BD. So first of all, it doesn't explicitly tell us that ABC and ADE are are similar. So can we show that ABC and ADE are similar to each other? And we can do that by looking at their angles. We can see that A is shared amongst the two, right? A is in ABC and ADE, right? Since ADE is nested within it, this A here has to be the same. So that angle is the same. And we can actually show that BD and EC are the same angles. If we remember to our grade 9, pretty sure it's grade 9 geometry unit, if we have two parallel lines and we have a transversal, right, remember this from grade 9, a transversal, the corresponding angles, or angles that formed an F pattern, remember that? F, Z, and C. Since you have these corresponding angles, we can say that B and D are the same angle. And similarly, E and C are the same angle. So we have all the same angles, so they have to be similar triangles. ABC and ADE are similar since all the angles are equal. Okay, so now that we have that, we can say, oh, look at this. Notice these three dots upside down instead of therefore. The three dots upside down like that, that means since. So since ABC is similar to ADE, we can come up with these proportionalities. So this is saying that DE, these are the ones that we know, right? DE is this guy here. DE is 21 divided by BC, which is 30. So this proportionality, since they're similar, we can say that that proportionality, the two lengths here, DE, BC, we know them. So we know this number, this fraction here. That's going to be equal to AD, which is this side, that corresponds to AB. Okay? So since, notice that AD and DE, those are on the same, they're both in the numerator. So they're both on the same triangle, ADE, and BC and AB are also in the same triangle. So they're also in the denominator. So just be careful when you set these things up that you have things in the right spot. So we can replace these numbers. I know AB is 36 from what they gave us. This larger length is 36. So 21 over 30. So that's the proportionality statement here for the two sides we know is equal to AD, the side we don't know, this shorter one, AD, divided by the one we know, which is 31. So now I have this nice proportionality here. To solve it, I just have to cross multiply. So 36 times 21, right? We multiply across the diagonal, and then you can divide by the third number. So it's 36. If that's confusing you, that's just cross multiplying, right? 36 times 21 would be equal to 30 times AD, but then I divide both sides by 30. So I just save some steps here. Anytime you have a proportionality statement, let's say 3 over 2 is equal to x over 8, we multiply across the diagonal and then divide by the third side. That's the way I always remember it. Makes things easy. So 36 times 21 divided by 30. So we end up with a side length AD of 25.2. So that's telling us this guy here is 25.2, even though the larger side is 36. Now the problem here is we still don't know what the side length of BD is, but that's just going to be the difference between the two. So BD is going to be AB, the larger length, to subtract the smaller length. So BD is 10.8. Sorry. So the length BD is just 10.8. Okay? So there, we were able to prove that they're similar. Then we were able to use that similarity to come up with a proportionality statement right here, because we know that the side lengths are proportional, and then it was just a matter of algebra to solve it. Okay? Now, there is another rule about similar triangles. We're not going to prove it exactly, but it's just you can, if you take the two triangles and make an altitude, cut them in half, and then don't worry about it. There is the other rule is that if we have two triangles, A, B, C, and D, E, F here, these two triangles are similar, then the areas, the proportionality of the areas is going to be equal to the proportionality of the corresponding sides squared. Okay, so the proportionality of their areas, area of ABC divided by area of DEF is equal to the corresponding sides, so let's say A and D, their proportionality, but squared. So A over D all squared, or A squared over D squared. Okay, so there's a third rule really of similar triangles. And how do we use it? So let's say I have two triangles, ABC and DEF. And it tells me that the two corresponding sides, AB and DE, notice AB and DE are corresponding because they're listed together. The first two letters are AB, and the first two letters here are DE. That implies that these are corresponding sides. So we can put them together in our proportionality statement. So this would be like side A, and this would be side D, let's say, or something like that. Well, actually, this would have to be AB would be C, actually. Let's go back here. Notice this would be AB. So, sorry, AB. So we can actually label AB as C. Don't worry about it, though. Okay, it would be C and F. But anyways, we can then come up with our proportionality statement. It doesn't matter that I used AD, not CF. I really should have used C and F here. Not a big deal. They're all going to work out the same thing. But we know that the area of DEF is 36, so I plugged in 36, and I plugged in 10 and 12 into my side lengths. I'm going to square them, and then take the then cross multiply again. So 36 times 10 times 10, which is 100, divided by 12 times 12, which is 144, which works out to 25. So the area of triangle ABC is 25. Okay? Awesome. All right, so that's pretty much it for both lessons 13 and 14. You know, for lesson 13 basically focuses on how do we prove that the two triangles are similar to each other, and then lesson 14 is it's more problem solving involving similar triangles. Okay, so now that we got this, next one, lesson 15, is going to be starting trigonometry, which is some of the exciting stuff that we get to do in grade 10. Okay, so we're nearly there. We're nearly finished the course. There's only going to be 2 more videos after this, 2 more trig videos. Lesson 17, the last one, isn't going to have a video because it's sort of like a summative type, not summative, but sort of put it all together type problem, type lesson. All right, okay, so best of luck to all you, and I'll be seeing you soon.